A star changes over time through a process called stellar evolution. A star can have a lifetime that is substantially longer than the universe. As Hugh said, this entire process of stellar evolution is by natural process alone. We do not have to invoke divine intervention at any stage in the history of life cycle of the stars that we observe. Sun is an example of a star, a medium mass star, and it is a great maker and source of elements. Hydrogen and helium are by far the most abundant element found in the sun. But what will happen when the sun loses its hydrogen? This is where the process of the star's life begins until it dies, from a nebula until it became a black dwarf.
Stellar nebula. It may look like a colorful work of art, but it's really a giant cloud of dust and gas. A nebula can take many different forms and shapes. But where did these stunning dust clouds come from? Some nebulae come from the gas and dust thrown when a dying star explodes. How does a nebula make stars? Well, nebula are made of very spread out dust particles and gases, mostly hydrogen and helium. Gravity begins to pull clumps of dust and gas together inside the nebula. Then, as those clumps grow larger, their gravity gets stronger. Eventually, a clump of dust and gas gets so big that it collapses from its own gravity.
During this stage of star existence, the radiation and heat from this reaction prevent the star collapse by the force of gravity. The main sequence stage of the photostar's life begins when it begins fusing hydrogen. Because fusion is temperature sensitive, it only happens in the hot, dense central region of main sequence stars where hydrogen is fused into helium. Hydrostatic equilibrium exists for all main sequence stars, including the Sun. Once a photostar starts burning hydrogen in its core, it quickly passes through to the Lyra stage in a few million years and becomes a main sequence star. During this stage of our universe, the majority of stars are galaxies' main sequence stars. Sunrise stars of star can vary in size and brightness, but the reason why all of them are considered main sequence stars in that day are converting hydrogen and helium in the cores, thus releasing huge amounts of energy. When the supply of hydrogen in the core starts to run out, the star can't grow hot from nuclear fusion. The core is becoming unstable too. The outer shell of the star starts to expand when its hydrogen starts to expand. While it's getting bigger, it's getting cold and becoming red, and it's called a red giant star.
If a star is a medium mass star like the Sun and it runs out of hydrogen in its core, it'll become a red giant star. Facts. Why are red giants bright but cool? This extra energy production will cause the outer layers of the star to expand even while the core is collapsing. In this bizarre geometry, even though the interior temperature is far hotter than on the main sequence, the outer layer expands and cools, producing a red giant. How hot is the core of a red giant? The red star will continue to heat up until it reaches a heat of 107 Kelvin, hot enough to begin fusing helium to carbon. Even our sun can and will turn into one when the time comes. Scientists say that it will begin this phase after 5 billion years. Not all red giants appear red. Sometimes other red giants may vary from reddish orange or yellow and white. Red giant stars are also can be called red giants in space. Is a dying star, the element helium will continue its fusion, which can form heavier elements like beryllium, carbon, and oxygen, and it continues to enlarge. It will explode and the next process begins.
Planetary nebula. Planetary nebula is a class of bright nebulae that are expanding shells of luminous gas expelled by dying stars. It is formed at the end of the life of a star with a mass of between 1 to 8 solar masses. The size of the planetary nebula measured at around 1 light year across. The density decreases as they age and expand. Its glow is due to the ionization of the ejected atmosphere by the ultraviolet photons, causing the dust and gas to shine. This causes a shell of nebulous gas around the central star to glow brightly. The lifespan of this type of nebula is around 30 years. As a planetary nebula phase ends, the star becomes a white dwarf, and the expanding gas cloud becomes invisible to us. This gives us an indication as to what will happen to our own sun when it gets to the ends of its life.
A white dwarf such a star have burned all of the hydrogen they have once used as nuclear fuel. Fusion in the star core produces heat and outward pressure, but this pressure is kept in balance by inward push of gravity generated by a star's mass. The vast majority of white dwarfs are formed after a dying star has shed in outer layers to form planetary nebula, leaving behind an approximately Earth-sized inner core that is the white dwarf.
On the other hand, when a star is a massive-sized star, and if it runs out of hydrogen, it will become a red supergiant star. Like red giant star, the fusion will continue, but heavier elements than beryllium, carbon, and oxygen will be formed. These heavier elements are neon, silicon, to iron. But when the red supergiant collapses because the fusion is over, the biggest explosion will happen. And when it happens, Earth would probably lose its atmosphere and all life would perish. But to avoid this situation, Earth would have to be at least 50 light years away from the exploding star. This biggest explosion is called supernova.
A supernova, known as the death of a star, is a massive explosion that takes place at the end of a star's life cycle. Massive stars that fuse matter up to iron explode as they die. On Earth, this is also visible. It's a supernova. A dim star can instantly have the luminosity of an entire galaxy. However, this intense light only lasts a short time, usually no longer than 2 minutes. What causes this to happen? A huge star cools down as its fuel runs out. As a result, the energy of the fusion's external pressure decreases. In the conflict between gravity and external pressure, gravity prevails. The star then explodes. A supernova's core would only be 30 km across in only a few seconds. The star's outer layers erupt due to the rapid collapse, leaving a dense core, usually a neutron star or a black hole, behind. In this explosion, elements beyond iron are formed, which are not usually formed in the core of stars. Supernovas have extremely high temperature that can reach billions of degrees. This drives the additional nucleosynthesis of new elements, heavier than iron. According to the latest research, most of the iron on Earth comes from these supernova explosions, not from the star's core.
From iron, element 26, to zirconium, element 40, which is far heavier than iron, the supernova produces a variety of elements.
Neutron stars are formed when a massive star runs out of fuel and collapses. The very central region of the star, the core, collapses, crushing together every proton and electron into a neutron. If the core of the collapsing star is between about 1 and 3 solar masses, these newly created neutrons can stop the collapse, leaving behind a neutron star. A black hole is a region of spacetime where gravity is so strong that no particles or even electromagnetic radiation such as light can escape from it.
That is the life of a star, from a nebula that became a fully grown star and will become a black dwarf or black hole when it explodes. Everything happens for a reason, like the collapsing of a star. When it collapses, it gives us elements that we can use for our daily lives. Everything has its ending, even a star that can live for many years.